So we've had just 3 talks which all have the word quantum and authentication in the titles. So maybe a bit more of an explicit title would be authentication and encryption of quantum messages with key recycling. So as Serge Fer said, this changes a lot from his talk where he was talking about classical messages with the quantum cipher. Here we're talking about quantum messages. And so what I'm going to talk about is just a new analysis for the family of quantum authentication codes from Barnum, Crépeau, Gottesman, Smith, and Taub, so from 2002. So I'm not going to propose any new protocol. I'm just going to go over their protocol and give you a new analysis of it. What I'm going to prove is that all the key can be recycled upon accepting the message, but this only holds for a subset of the family of QMAX, of their protocol. So I'll explain at the end why it doesn't actually hold for all, because they actually prove security for a big family of protocols. And part of the key can be recycled upon rejection as well. This is optimal. We can't recycle anything more upon rejection. And I'm using, well, the composable framework that I talked about this morning in the first talk. So key recycling is actually not a quantum phenomenon. You can recycle in the classical case as well. This was already noted by Vergren and Carter in 1981. So here's a simple example of how you can recycle key in classical authentication. You have your message X, and Alice wants to send this to Bob, and she's going to hash it and apply the, append the hash to the message. So she sends X with this tag, which is a hash of the message. But then she's going to one-time pad this tag, and she sends this to Bob. And Bob, upon decrypting, well, he undoes the one-time pad, and then he checks if it's the right hash, and then he'll accept or reject depending on that. Now, the idea is that since this part of the tag is hidden by this part, Eve is listening to it, and she's not going to get any information about it. So she gets no information about K1, so you can recycle K1, you just need a new K2 each time you use it. And when you think about it a bit, it's kind of obvious. If you send n bits of information, Eve gets n bits of information about the key, so you lose n bits. And you can't do anything better in the classical case. In the quantum case, if you try to draw an authentic channel, so kind of the basic idea of just authentication, if you don't see whether Eve can cut the channel or not, just Alice sends a message and Bob gets a copy and Eve gets a copy. She just can't influence it. If you try to draw this in a quantum picture, well, there's some immediate problem. You can't clone. So there's not such a thing as a quantum authentic channel. At least there's no viable definition in the literature, and I wouldn't even need to go about it. Because if Bob gets it, then Eve doesn't get it. So however you try to define it, you'd have to be fundamentally different than what people mean by an authentic channel in the classical case. So whenever you have a scheme which guarantees that Bob gets the message which was sent, as a side effect, it guarantees that Eve has no information about the message which was sent. So just trying to authenticate a message, you end up encrypting it. Right, so the idea behind the key recycling, the reason why we have some kind of advantage in the quantum case is basically this. If Bob can verify, now he has to verify he received the correct cipher, which is not the same as verifying he received the correct message. If he can verify he received the correct cipher, then Eve has no information about it, so she has no information about the key, so the key can be recycled. So it's roughly the same principle as QKD, so it's not really a surprise that this actually works. So how do we do it? Well, let's start with something, the quantum one-time pad. And let's suppose we're running the one-time pad, we have this insecure channel. So Alice basically gets a message, and she applies the one-time pad depending on her key. So these are just the Pauli operators which depend on the key, and she sends that. And we have some Eve down here that changes the cipher and puts something else in. And Bob decrypts it, and he's going to get another state out there. And now, what do we do? What does this one-time pad actually do? So what we can show is that what we end up is some kind of channel which doesn't give Eve any information about the message which was sent, just maybe some bound on the size, but it allows her to modify the message by applying Pauli operators. So if you do this in the classical case, the classical one-time pad allows Eve to flip bits of the message. In the quantum case, this allows Eve to flip either bits or phases of the message. So how do I state that formally? If you were to talk this morning, you've probably got an idea, so I'll just go through it quickly. We want to say that our protocol constructs this channel given these resources. And the way we're going to define this we're going to say that the real system, which is here, is a subset of an ideal system, where we also allow Eve to do whatever she wants at her interface. So if we just take the set of this over all possible operations that Eve could be doing here, and we just want the real system to be included in that. So if you now plug in quantifiers, and you see all these calligraphic letters are sets, we're basically saying for any sort of implementation of the secret key in the insecure channel here, there must exist some malleable channel and some simulator here such that this is equal to that. And the way you prove this is actually with a very nice simulator, which just picks a bell pair, sends half of the bell pair out, and you get something back, and then it's going to do a measurement in the bell basis. And then you get a string, and the string that you get from your measurement, you put it in here, and the corresponding flips are done there. And these two systems, as long as the messages go always in this order, first there, then it comes out, then you put that in, then it comes out. If you do the same thing here, these two systems are equal. You can't distinguish one from the other. So you can really show that anything Eve can do here can be reduced to these bits and phase flips. Okay, so now we have our malleable channel, and we would like to construct a secure channel. And if you were there in the talk this morning, I was saying how doing authentication doesn't work. So we're not going to do authentication. We're going to try and do something else. So if we have a malleable channel, it means that Eve can do some Pauli errors. So what we need to do is catch Pauli errors. And how do you catch errors? We'll use a code. So the idea is you take your message row, and I'm going to apply some kind of encoding to it. So I just append it with some ancilla in the state 0, apply some unitary, which is going to encode it into a larger space. This goes through, it gets, Eve can do bit flips or phase flips on it, and on the other side, Bob is going to undo the unitary, and then this is just supposed to be some measurement. He just measures the last qubits here, and it's going to get it's going to get projected onto S. And then if S equals 0, then Bob accepts, and if S is not equal to 0, Bob is going to reject. So we're going to do this with a family of codes, because of course if Eve knows what code we're going to do, Eve can just input some error which the code is not going to catch. So the idea is we want a large family of codes, and we're going to choose our codes in such a way that with high probability over the family of codes, we catch all errors. So we're going to do it with stabilizer codes, which have this nice property that when you apply the code and you do a Pauli and you then decode, this is going to map this Pauli error to another Pauli error. So all this is going to be equal to some Pauli error, which is either going to modify this state or modify this one or both. So now all the errors for one specific code K, all the errors, you can put them in two bins, those that get caught and those that don't get caught. So they don't get caught if they modify only this and they do only phase flips on this part, and they do get caught if they do bit flips on this part. So now for every code, we can say, okay, this is the set of errors that my code is going to catch, and we want to choose a set of codes such that with high probability we catch all errors. So now we can formally prove that this actually works. Given this malleable channel, we want to prove that we construct a secure channel. But now we don't do it perfectly, so I have to introduce a notion of distance, which I already quickly explained this morning. But for any system, we can just define a metric between the systems based on how well a distinguisher can distinguish between them. So now what we want to prove is that our real system is included in our subset of our ideal system, where we put some epsilon ball around, where this is defined with our the metric. Written up this way, we just want to prove that the real system is indistinguishable from some ideal system, where we just have to pick this right, and you have to find the right simulator here. And this is easy to show with a very trivial simulator. Simply, I mean, here you have to just output the constant, which is the size of the cipher, and you get E, and if E is equal to 0, you let the message through, and if E is not equal to 0, you don't let the message through. Okay, so trivial simulator, and you can show that that the distinguishing advantage between the two is just epsilon, which was the parameter from the code. So now we can compose the two steps. You can do the one-time pad followed by the code, so it just looks like this. This would be the one-time pad, so you use your first key and send on the insecure channel, and this is then your outer protocol where you do the you do the code. And then the composition theorem basically says that what you get is a secure channel, and you can compose your two simulators to get a new simulator. So when you compose the two, the composition of the protocols gives you this, and just you have your simulators which are composed. So yeah. So for technical reasons, the proof is not done in 2 steps. We have to do it in 1 step if we want to actually prove this, because there's actually a second strategy from the distinguisher, which is you could input something there, it comes out here, you input it there, you come out there, or you could first input something here and out there, and then you put the message in there and put it out there. So the distinguisher really has 2 strategies, and the decomposition I showed you, it actually only works for one of the strategies. So instead, we just give like a one-shot proof like this. So the protocol composed together, you just assemble, you add your state 0, you do your code, you do the one-time pad, and then you decrypt, you undo it, you measure, etc. So the protocol says you accept or you reject depending on the value of S. Okay. So now we want to recycle key. So that's the protocol without key recycling. If you recycle key, well, the intuition is the one I explained at the beginning. Here we have this unitary for the code, and we have the one-time pad, which is done after it. So K1 should be hidden by K2, so we should be able to recycle K1 no matter what. It turns out that this intuition is not sufficient, because it's still possible that the bit of information here, whether we accept or reject, leaks some information about K1. Well, I'll show you a nice example which actually does that. But with the scheme that I showed you, it actually works. You can recycle all of K1. Always, whether the message is accepted or rejected. And if Bob receives the correct cipher, then Eve has no information. Sorry, that's what I just told you. If, so you can, yes, this one can always be recycled, and sorry, K2 can be recycled upon accepting. But now for Q, as soon as we model this, you realize there's a little problem. Bob must confirm reception of this to Alice before recycling before Alice can recycle the key. Alice has to know that Bob has received it. If Alice recycles her key too soon, uses it in another protocol, the adversary might get it, and then be able to break the authentication scheme, which is being used here. So we're going to need a backward authentic channel. So we have to change our real system here if we want to do key recycling, so that we have a secret key and we have a backward authentic channel with just where Bob will just send one bit of information saying, it's okay, I've received the message. And he says whether he accepted or rejected it, so Alice also knows how much key to recycle. And then Alice does that. When she gets the bit from Bob, she's going to either recycle all of the key or just part of the key, or she might not get any message, and then she doesn't recycle anything. Like if she might get an error from the authentic channel, in which case she can't recycle. If she just gets an error, she doesn't know why she's getting the error. She doesn't know if Bob has actually received it, and then she can recycle it, or maybe Bob has not received it at all, and it is Eve is trying to inject stuff on this authentic channel. So if Alice gets an error from the authentic channel, but there's nothing she can do, she has to throw everything away. And then Bob can either recycle all of the key or part of the key. So this would be the real system, and in the ideal system, we now have a new key resource. So what we want to prove is that we have a system which generates a fresh key, and Eve has the corresponding controls over it. She can decide the length of the key, because here she can, of course, decide to introduce noise or not, which then means that they can either recycle all of the key or only part of the key. And then Eve also gets to choose if the message on the authentic channel is actually received or not. So she gets to choose if Alice gets the key or not. So there are these 2 bits that Eve is allowed to input on the secret key resource. This is just repeating what the protocol is, encrypting, decrypting, and then depending on the value of S, you either recycle everything or you just recycle part of the key. So what I've just done here is argued is the quantum authentication part, where we start off with these resources. So we have a key, we have a backwards authentic channel, and we have an insecure quantum channel, which are these 3 resources. And we construct a secure quantum channel, and we get the key back. So the key here, we get it back, but with an extra switch on it, which is just not drawn in the picture. How much time? 4 minutes, thank you. And the theorem says the following, that this works, and you get an error which depends on your parameter here for the family of codes. So if you catch the error with probably epsilon, you're going to catch the errors. Then you get an error delta, which depends on the square root of epsilon. So the distinguishability between the 2 systems depends on the square root of epsilon. That's it. So you can now instantiate this, because this is a big family. We just said we just need to plug in some code. So there was a code which was proposed in the original paper, which kind of has very short key length. If the message has a length m, and we add n qubits for the syndrome, key k1 has length n, and key k2 is roughly 2m plus n bits. So this is kind of small, and then this is the error we get. We can also plug in unitary 2 designs. And then you need a bit more key at the beginning, but then you're going to get all this key back when you recycle it. And then you get a better error. So it's some kind of trade-off between how much key you start off with and the kind of error you're willing to accept. So the kind of codes I used here were actually stronger than the codes you find in the original paper, because the original paper doesn't say you have to catch all the errors with high probability. The original paper says you have to catch all the errors which don't modify the message with high probability. So there's a subtle difference, but they aren't trying to verify that you got the right cipher. They're trying to verify that you got the right message. So for every codes, you could divide the errors into those that change the messages and those that the errors which don't change the message. They're just going to mess with your syndrome. They might just do a phase flip on the syndrome, which no one will notice, and actually no one cares. So as long as you're just trying to get the right message, you don't care about these errors which do a phase flip on the syndrome. But the result is that you might receive a different cipher and you don't notice. You just get the same message. So this is actually strictly weaker. And this only guarantees that the message is not changed, not the cipher. So you can actually have very specific attacks, and you can construct it. For example, there's some codes. I have it on the next slide. There's some codes which use this, and you can construct some kind of attack where Eve is going to pick an error in this set, GK. So this is the set of errors which don't modify the message. So it's in this set for, say, half of the code, and it's not in this set for the other half. So then when Eve looks to see whether Bob accepted or not the message, Eve will just have learned a bit about the code that we use. So even though the code is one-time padded, just by looking at this bit of whether Bob accepts or rejects, Eve learned something about the inner code. So that's why you can't recycle all the key by using this weaker notion of purity testing codes. So there are a bunch of other quantum authentication codes which have been proposed in the literature. For example, there's this signed polynomial code, which has exactly the same structure as the one used in the Barnum and all paper, but it's on qubits, not on qubits. And the proof which I wrote up is written up for qubits. So this most likely goes through, but I don't know. There are a few other codes. The Clifford code falls in the same category, so proof goes through. The trap code was the one I mentioned, which uses weak purity testing codes, and here you can show that you cannot recycle all of the key, but my conjecture is it only leaks 1 bit of the code. There are other protocols which have been shown to recycle part of the key, and it isn't quite clear if you can recycle all of the key. So now, what I've done so far is assuming there's absolutely no noise on the channel. And what if there is noise on the channel? Well, so if there's natural noise, there's not an eavesdropper. We really want our protocol to work in the case of natural noise. So what we do is, obviously, we just apply an error-correcting code. And this is something which we can do in this case because we assume we have quantum computers, and Serge Fehr couldn't do in his case because he doesn't have quantum computers. He really wants a prepare and measure protocol. So noisy channel, an error-correcting code produces a noiseless channel. And if you apply to an insecure channel, you just get back an insecure channel. And there's another thing. We needed a backwards authentic channel. And the problem is the backwards authentic channel requires key. So we spend key on that, which we're not recycling. So I've been telling you we're recycling all the key, when in fact, to construct the backwards authentic channel, we need to spend some key. There's a very easy trick. If you have a secure channel, you just use part of your secure channel to send a message, and the other part to send key to replace the key used in the backwards authentic channel. So this would be a scheme like this. You start off with a secure channel for 2 messages, and you get 1 key out of it and another secure message. So if you start composing it, this is the main part of the protocol, and you can construct an authentic channel to get your authentic channel here, and then you can you can get more key out of it to replace the key which is lost here, just identity here, and then you can use error correction to construct noiseless channels for noisy channels. So you start off with just key and noisy channels, and you end up with key and an insecure channel. And this is what the composed protocol just looks like. You have all these little parts you put together, and you end up with some composed protocol. Thank you.